I was MEMS design engineer for 2 years at IMEC, and we're going to talk today about PMUT arrays. So piezoelectric micro machine ultrasound transducers, which I did design for about 2 years. And there were lots of things that would just not be sufficient in terms of simulation capability. So whenever you wanted to simulate crosstalk in an array of more than 5 by 5, this was game over. It would just not work with a off-the-shelf market products. And well, this is enough sometimes, but it's not always enough. And I'll show how we can actually leverage cloud computing to either speed up existing simulations that would take too long, or access to larger capabilities in terms of simulation size, so larger arrays, for example, but also run many simulations at the same time to just get more sweeps done through in the same amount of time, and so more explorations. And what we provide at Quanscient is Allsolve, this product, which is essentially a really general multiphysics solver. So it's not limited to acoustics, and we scale it in the cloud. So we have scaling algorithm, and actually it's not enough to have access to the cloud hardware, which is pretty unlimited. You also have to scale in the cloud. This is what we do, so we can get more than 100x speed up, and we have written papers on that in a wide range of areas, such as superconducting, nuclear magnetic plasma confinement, or electric motors, or MEMS devices, or whatnot. So the type of things we simulate is very varied, and I'll do live demos after a bunch of slides. I will show this actually in the 16 by 16. I'm also running a 24 by 24 a PMUT array now, strongly coupled piezoelectric, acoustic, and mechanics. But we can do lots of other things, such as like actually solving the Navier-Stokes equation to get your MEMS damping, and not having to necessarily go to like a lumped modeling of the damping, like squeeze film damping. We can do thermal mechanics for packaging on large scales really well. We can also do RF devices, so like surface acoustic wave devices, or like F bars, whatnot. Here an example of an F bar. But then also lots of other different fields, such as here full-scale nuclear fusion stellarator magnetic field simulation for some of our customers. Lots of other features that we are the only ones to provide, such as multi-harmonic method, the harmonic balance, which allows you to solve in the frequency domain nonlinear problems that you would otherwise have to transient through to get the steady state response in other software. We can do that in one go in the frequency domain. So whenever you have a high Q value, this is extremely beneficial to just be able to get the solution. Lots of other examples. I will not go through all the details of those. So I will right now immediately jump into the live demo. And well, let's see, this is a bit on the kind of dangerous side for me, but I have this 24 by 24 PMUT array, out of which I will start as first step simulating a single PMUT array live, and then I'll go to a larger array, I think 6 by 6 with a frequency sweep, to demonstrate the like embarrassingly parallel capabilities of the cloud to run many frequencies at the same time. And then I'll actually run this 16 by 16 PMUT array, unless this one like works as expected. But you can see it's running right now. So far on this one, actually, we push it further. We have 68 million unknowns, 3D FEM. Let's see. Yeah, cannot guarantee anything on this. I've never run a 24 by 24 PMUT array, but so I'll come back to you if that one works. Otherwise, I'll run a 16 by 16 as agreed. So let's start with the most simple 1 by 1 PMUT array, to really understand how to set up things, also to demonstrate how to import GDS files. So this is my browser. I don't have to install anything. I don't have to own expensive hardware. A laptop is enough. And yeah, we have lots of, well, I won't talk about the licensing, but it's very different. You can have as many users as you want at the same time. You have no limitations on how much hardware is available on your desktop computer, because it's not running on your desktop computer. It's running on Amazon Web Services in the cloud, in this what I'm going to show you. You can have lots of nicenesses, such as sharing a project is just sending a link and giving accesses. So you don't have to juggle with heavy files that you have to send by email. So just the fact that it's a browser-based product makes it very convenient in many ways already. And besides this, we also have access through APIs, and we have an SDK to access through the API. So if you want to integrate that in a workflow to automate your simulations, you can do that as well. But here I'm going to show you the graphical interface only. In terms of demo projects, we have a wide range of things, from magnetics to PMUTs to RF for PCB, S parameter calculation and whatnot, and they're all available here to get started easily. But enough of kind of summarizing the product at a high level. Let me start with the actual run of a single PMUT first to start. So yeah, let's call it PMUT demo 1 by 1. I create my project. And then you have the option to import a step file or GDS file, GDS2, or right away a mesh file or a Nastran file that you might have exported from some commercial software. So you can work with mesh files and just drag and drop here, and then you continue as if it were a CAD file. Very convenient. Here I'll pick the PMUT array 1x1.gds. And yeah, and then, well, you have access, that's worth mentioning, you have access to everything. We don't have modules, so you don't have to buy a GDS import module, whatever. Everything is always included in the package. So the thing you do first is you have to stack up the layers. So these this has been drawn in K layout, and you have the numbers 1, 2, 3. You stack them up in the right order. You provide the thickness of each one. So I'm not gonna lie, I have a cheat sheet on my other screen, because I don't remember all these numbers by heart. So you stack them up and you provide the layer thickness for each, and then you build that. We'll see how the PMUT looks like. This is how the PMUT looks like. So it's arguably not the most general and advanced model, but nevertheless, it has a membrane, a cavity, piezoelectric layer, which I don't know in this case, but typically is best at 67% radius of the membrane, but this will do. And then what we need on top then is, here we're not going to simulate the substrate elastic wave. The focus will be on the acoustics on top, but we can do both. So what I'm going to do is I'm going to add an air layer on top, and I will show you kind of a little bit more advanced tools like periodicity, just to simulate a quarter of the PMUT. Yeah, so let me at the same time illustrate a bit, besides the importing the GDS file and step file, what you can actually also do in terms of CAD operations right in the browser. So we don't provide a full-blown CAD engine, but nevertheless, we have quite a bunch of convenient tools. So what I'm going to do, I'm going to create a sphere, and I will intersect it to end up with a PMUT with a quarter or an eighth of the sphere of air. So I draw a sphere, and then I'll add 2 boxes to create some intersections to illustrate how this all works with the Boolean operation. So I'll create a box of given size that you can, if you want, you can parameterize it. But here I'll just hard code the numbers. And then once this is done, so we have 1 box that we need, and then we're going to draw another box that's just the same, but we will shift it a bit in the Z direction so that we can access. So we have the actually the air starting on top of the membrane, and the piezo layer is actually in the air because it has been etched away everywhere else. So now we're all good. We can ask to break this all down into pieces with the fragment all operation. And then what we're going to do is we're going to get rid of what we don't want to see. So this. You always need to be able to access what's inside. So this is how you do it. You hide it. If you want to see the scale, you can do that as well. Yeah, and then we still need to erase these pieces of PMUT, and this is empty below, so we're good to go. And we have principle, we have our quarter PMUTs. There we go. So this is one way to obtain it. You can of course import a step file right away, or any other method. So let's go for that. Let's set it up. So we're going to create what we call shared expression. So if we want to make a frequency sweep and run all these frequencies at the same time, then we need to define a variable that is the frequency that will be known to the system. Well, system-wide, you can use now the variable frequency, and by default, it has a value 1 megahertz. But I will override it and make a frequency sweep in just a second. Then you assign materials. You can see we have a bunch of materials predefined, especially for the MEMS domain, such as the monocrystalline silicon that I will use here with the actual anisotropic material property. And by the way, you can rotate the crystal just the way you want if you don't have a standard orientation of, for example, your PZT material. We'll see that we'll use the PZT material in just a second. So I will just, as you would expect, assign the materials. So this is air. That's it. You can see the properties if you want to change them. For example, if you have some RF simulation and the permittivity, for example, is temperature dependent, you could just change it that way. You can make it anisotropic or not. You can make also, well, we'll see that for the silicon, which is actually anisotropic. Next step is we'll assign PZT to the PZT layer here, which I have to select a volume. You can see that the PZT, you have an elasticity matrix that's like anisotropic, the different, or orthotropic with a different Z value. You also have the same for the piezoelectric coupling matrix, which you can edit the way you want. And by the way, this will all lead to an automatically generated high-level Python script that I will show you at the end. But everything I do graphically populates a script that you can modify the way you want. And you can also use in the API as a to run your simulation. The next step then is to define the rest, which is in my case assumed to be monocrystalline silicon. And this consists in basically these two pieces, and then we're good to go. And you can probably recognize that elasticity matrix of silicon, which is from that very famous paper, What is Young's Modulus of Silicon? So this is the silicon in the standard wafer orientation, but you can rotate it again, as stated, if you want. Next step, what we could do if we want to probe the mechanical displacement and make a plot versus frequency, we could define a point region here. So we will select a point. Has to be a bit accurate, and then we give it a name, for example, the center of the membrane. And yeah, then we're all good to go for the physics setup. So in the physics setup, here it's a 3 physics strongly coupled simulation. So we're going to have what? We're going to have solid mechanics, we're going to have acoustics, acoustic waves, and we're going to have electrostatic simulation. So you could, of course, do current flow as well, but typically electrostatic works well, and you can also get the number of charges, capacitance, whatnot there. And I won't show that, but you have lots of options, such as if you have large displacement or if you have pre-stress, you can include this all here quite trivially, which is pretty critical because it's always the case due to fabrication. Next step is to set up the physics. So very easy. Solid mechanics doesn't apply everywhere, so we have to say that it applies where it applies. So for example, we could hide the air and select everything that's visible. So solid mechanics is only applicable here. Acoustic waves, it's applicable only in the air here. And electrostatics, well, in a very good approximation, it's actually only applicable here. So now we're good. Just double checking, yes, yes, and yes. Checking the time as well. Yeah, then we set up the boundary conditions, which we call interaction here. And by the way, this is the whole set of physics we support. So pretty much anything you might want to do is supported. And you can extend it in the scripting interface. Solid mechanics, we want to have piezoelectricity, which is here. Where is it applicable in the piezoelectric layer here? And then we want to set up also some clamping boundary conditions. So several ways to do this here. Kind of assume that it's it's not, well, different clampings give you slightly different results. You could just clamp the whole surface everywhere around it. I could also just clamp the bottom. This would kind of mean that it's edged all around, which is not the most physical, but I could just clamp this as well. Doesn't matter that much in this demo. Last step for the solid mechanics is to make it aware that you actually have a full PMUT, but you're simulating only a quarter of it. So I could use symmetry or periodicity. So let me add periodicity. So I'm just going to say that this phase maps to this phase through a rotational periodicity around the center, which is at 0, 0, 0, and actually positively 90 degrees around the z-axis. That's it, and we have now the solid mechanics set up. Acoustic waves, easy to set up. So we're going to add acoustic structure interaction. That's it. And then we also need to tell that the boundary, the waves can leave the domain. So we could use a PML, or in this case, because it's a like source pretty far from the boundary, we could as well use an absorbing boundary. Both cases are really easy to set up. I think in the 16 by 16, I use a PML. But here, like if I wanted to use a PML, I would just select the surface and it will grow me the structured mesh on top to have optimal PML absorption. But if I don't want to do that, I could as well here use an absorbing boundary condition, and then I will select it here. There's no need for any periodicity for acoustics because it's just naturally going to be periodic and symmetric. And then the last step will be to basically set up the electrodes on the electrostatics. So we're going to have two things. One thing is a ground electrode, which is the bottom here with a 0 electric potential. And the other one will be, well, either I put a sine wave at the top, or if I want to be able to easily compute the total charge at the electrode, I can choose this lump PQ. And this will lump my electrode, and I will have access to the charge and the voltage. If I want to compute capacitance, that's the way to go. What I could say is that I want to drive with a sine wave with sine 2 pi ft. In the transient case, you have access to lots of functions like wavelets and ramps and whatnot. But here it's a frequency analysis, so I'm going to use this sine 2 pi ft. Let me just quickly go through to be sure I don't have a demo effect, I didn't miss anything. Piezoelectricity there, clamp there, very good. Periodicity also. Acoustic wave, absorbing boundary, yes. Electrostatics, and then we have the ground at the bottom and the electrode at the top here, yes. So we're all set, and we can move on to the simulation section, for which I'm going to create a mesh. Now, I cannot necessarily use the defaults. I want to be able to guarantee that I capture the waves with a fine enough mesh for the max frequency I want to set up. Typically 5 cells per wavelength will be accurate in this this software with second order acoustic interpolation. So I can set up well, expert setting mesh refiner, so it will refine a bit wherever you want. We can also do mesh extrusion for thin layers, like collapsing the stack of the MEMS and extrude it from a footprint. This allows to trivially mesh very thin layers that are typically a problem to mesh. Here it's not very thin, so it's not very needed. But I'm going to impose a max size of 1e-4 to capture the max wavelength in the acoustic medium that I plan to have. Then I ask to mesh this, and I can run a simulation. You can run any number of simulations at the same time. There's no limits because it's not running on your hardware. Now this is kind of this is the mesh that we got. Yeah, fairly fine enough on the acoustic side. You it's going to be accurate enough on the mechanics side, but you could as well, as said, you could use the structured entity or the mesh extrusion here if you wanted to actually get an extruded prism layer or hexahedra. That is all possible. This will do just fine. And then the next step is then to set the analysis type. So as said, we support steady state, harmonic, nonlinear harmonic, which is multi-harmonic, transient, or eigenmode analysis. Here we're going to do a frequency analysis, so harmonic. The frequency is parameterized as frec. And yeah, and that's it. You can choose what hardware you want to run on. So we will see if you need access to 1.6 terabytes, then you might just say, I want 100 machines of 16 gigabytes. If you have a small simulation like here, then you might just say that take the most basic machine and you're good to go. We associate the mesh to the one that we have created. And then what do we want to see in the end? We want to see the real and imaginary part of the mechanical displacement. But for example, if we just want to see the real part on the skin so that it renders faster in the browser and not actually everywhere in the volume, which is not of interest to me right now. And also the pressure field real part only on the skin region. And the last thing I might want to ask as an output in this case is what is the max displacement at the membrane, so the max UZ in in a complex magnitude. So for that I will cheat a little bit, but basically you probe at the point that I've defined and you take the complex norm of your mechanical displacement, the Z component. So pretty standard things. And at this point I could show the script that is automatically generated. So this is all automatically generated based on what I've done graphically. And this is the entire script. So if you want to understand what's running under the hood, or if you want to tune anything, then you can always go to scripting mode. And then you're ready to go into tune. You can tune any equation you want to tune. But it's fairly readable. And I think it must be so that we have one of the most user-friendly scripting interface in the markets. For example, if you know a little bit of weak formulation, or if you have tuned weak formulation in your in other commercial software, then this will be really really a dream. You can, for example, see here the inertial term for the mechanics, so the density times the acceleration of the field u, the displacement. So you can really add anything you want, any exotic multi-physics coupling. This is all possible, and you can output exactly what you want and automate exactly to get out just exactly what you want. So full tunability here from A to Z. But here we're not going to use it, just wanted to show that it's possible. What we're going to do here is we're going to make a frequency sweep, and this will be a first way to show you basically the ability to unroll sweeps and to just parallelize them by starting them on, here in this case, 40 different machines. So this is not a big problem, but it might still take a few tens of seconds to solve. That's pretty normal. I don't use a powerful machine here. It's just the most basic one core machine, but I want to run 40 frequency point between 6 megahertz and 10 megahertz equidistant in terms of spacing. And what I do is I click run, and you can see that all the frequency points start at the same time. And so for anything that takes a non-negligible amount of time to run, this gives you 40x speed up very trivially. This is one way to speed up by just having as much hardware as you want. And the other way to speed up things, which can also be combined to this case, is to accelerate each individual simulation. And this is what I'm going to show on the 16 by 16 array, for example. In that case, it's not really accelerating, it's just enabling it, because you might not have enough RAM available on your desktop computer. That for sure will not have enough RAM available for very large arrays. And we do distributed memory computing, so we have access to terabytes of RAM if you need it. But so everything started at the same time. You can check each job, what's going on, and you can see what you have asked to print in the scripting interface, for example. But we will soon start seeing the data coming back. So you can see that they are all running. Some are coming back, so we can go to the plotting, and you can see that the data comes in a pretty Gaussian curve way. So first a few and then the bulk of it and then the last slow ones. But basically the simulation is finished, and I have run now this quarter PMUT simulation with 40 frequency points very easily on 40 different machines of each one core. And if you want to see what's going on in terms of, for example, the pressure field, then we could visualize this. And again, here you have all the frequency steps that you have run, and you can see that as you increase the frequency, you will see that actually the wavelength decreases, but also the directivity changes. So you can analyze all the results very easily like this. And you can also visualize, if you want, the mechanical displacement, although here nothing really fancy to see because we're below, or actually we are below and after the first mode resonance, so you won't see fancy vibration of higher order modes. But you can visualize this as well if you want. So if I exaggerate a bit the displacement, then we will see the membrane vibration. And in principle, if I look at what's going on before resonance, I need to exaggerate even more. And before resonance and after resonance, you should see a phase shift of 180 degrees, which is pretty typical, and this is what you see here. But this concludes the first simple 1x1 PMUT array demo. And I want to be mindful of the time because it took pretty longer than expected. So what I'm going to do is I'm going to go through the 6x6 PMUT array, and what I will do is not do the full setup because this is going to take again 10 minutes. But I'll go through, well, how to set it up, and it's exactly the same way as what I just did. Except here, actually, I wanted to highlight that you can also draw it in the browser right away. Also, the 24x24, at some point it starts to be pretty slow, but then the API allows to let you go even further if the other rendering starts to be a bit slow above 24x24. But yeah, so you have lots of operations like translating, copy, and you can create easily arrays like this. The setup, same thing. Here I have parameterized the dimensions, which I have used here in a parameterized way, so I can change it easily. And the array size, I assign my material here a PZT, which is here. The rest is silicon, and I track also the pressure. This time I track the pressure at the top, just above the middle of the array. The setup of the physics is exactly the same, except here I've used the PML. And the PML is just a one-click setup, so you instantiate the PML and you select the surface and you're ready to go. I think I have less than 10 minutes, so I will not set it up as said. What I could do is make a run. So here I'm going to make a frequency sweep around the resonance, or not far from it. I will track what's the pressure at the top above the array for 41 frequencies here. And I think this does take, so I think I run with 10 cores, 10 nodes of each one core, so 10 machines with one core each. So that's it's not needed just to have it faster. That's 160 gigabytes of RAM available. It's not a big simulation, but it starts to be actually a bit on the edge of what I remember being able to simulate with off-the-shelf commercial software. The largest I've ever simulated was 5x5 actually. So this is not big, but it's also really not that small. So I think it's going to take kind of 3 minutes. You have a little startup delay because now you're using a heavier machine. It takes a little time to boot it up, but a few tens of seconds. And while this is running, I could show at least, because now I won't have the time to run it, we could see what this guy has done. So this is a 24x24 PMUT array. I think you remember as it was running, it was kind of here when I started the demo, and now it's finished, and it took 320 seconds for the run, a few more tens of seconds to load the mesh, but this was actually 68 million unknowns on 200 nodes of each one core. So this is equivalent to having access to 2 terabytes of RAM. But it's actually even better than that because this distributed domain decomposition techniques actually scales more linearly in terms of memory requirements. So if you would have used a direct solver, which is the standard tool in any software, then you would have actually needed much more than 3.2 terabytes of RAM. So you need less RAM, and you also have access to more RAM. And visualize, for example, the pressure field. Now I'm not so sure if I had a fine enough mesh. Otherwise, I'll just show it on the 16 by 16 PMUT array. So this takes a little while to download. I can already show the 16 by 16 because this is rendering now in my browser, which, well, it's not the fastest thing to do. But nevertheless, here it's the 16 by 16, and well, you don't see any pressure here. This is the top of the PML, so everything is absorbed. But you can see the pressure waves at the bottom, where you have the PMUTs touching. And you can see that you have pretty fancy directivity patterns going on due to the natural focus of the array. If you wanted to do phased array simulations, this is not difficult at all. You would have to do a very little math of like propagation distance to, for example, a pressure point. And then you would, for example, go to the electrode and you would be able to just provide a phase shift for, well, you might have to define, no, you wouldn't have to define each electrode surface individually. You might be able to just use an expression that basically measures at every point in the array what is the phase shift you need to apply to focus at the given point. And this phase shift in the end will be something that will be an expression, not a constant like here, but something that depends on the radius, the X, Y, Z coordinates, and what, you know how that goes. So that could be done as well pretty easily. How is this one going? I think it's starting. Wondering, I might have used quite a lot of computing power in my rehearsal. Let's forgive it. Let's see for this one. Yeah, so this is the 24 by 24. I have used a mesh that is a bit too coarse, but nevertheless, yeah, so I didn't promise anything on the 24 by 24. I will definitely run it with a finer mesh again. On the 16 by 16, what we could still do is actually plot also the mechanical displacement of each individual membrane. And then I will approach the end of my time, unfortunately. So we still have 15 minutes of Q&A time. Yeah, well, I say rendering on the browser is not the fastest thing, but there we go. So each membrane is actually modeled as the full cavity with the vibration, first mode vibration around here, and we could exaggerate a bit the displacement. Maybe that's a lot, but there's no parallel plate assumption done whatsoever. Yeah, and it's worth also mentioning that if you want to download the whole set of result files to visualize, for example, ParaView, you can do that by clicking on result and downloading it. If you think that the browser becomes a bit too slow for the rendering for large scale simulations, but it was showing and now I clicked re-render. But I think I'm approaching the end of the kind of scheduled time. And well, there we have it. So the displacement is not exaggerated enough, but basically you can see the membrane bending upwards. And that's about it. Like as said, we have lots of other types of simulations that I will not have the time to go through, such as, for example, PCB, RF, photonics, and one last example before I really conclude here could be to show something that I did, for example, a few days ago, the electric heating in some quantum hardware hanger resonator. So this is a building block of a quantum hardware. It's used for filtering. So this is a resonator. We compute S parameters, and then we also compute the heating due to the electric losses. And you can see for a frequency sweep, you'll see that at the resonance frequency of the hanger resonator, the hanger resonator starts to heat up, and you can plot the heating up for versus frequency. And you can also plot, if you want, you can plot the S parameters, which will look very much like the usual profile of filtering for hanger resonators. So we can do lots of other things as well.